Hello everybody and welcome back. We're still looking at the 2016 open paper and we are on C3. There we go. So, let A be a point at, let's be very clear, we're on C3, now the line isn't going through anything. So A is at 0A, O is the origin, C is at C0, and B is at CB. So B is sort of just above C. Or maybe just below. No, it's got to just be above because A, B, and C are positive integers. Okay. So let P be at P0, so on the x-axis, be a point on the line segment OC that minimizes the distance AP plus PB over all choices of P. And let x be the sum of the distances AP to PB, so that minimized distance. Okay. Minimizing, now that's interesting. So that sounds like an optimization thing, so we might be looking at an arithmetic mean, geometric mean to find this point. We certainly don't want to use calculus or anything like that, but we'll draw a picture and deal with that in a moment. A, show that this minimum distance is c squared plus a plus b squared, and we'll take the square roots. This looks like a distance formula that's going to simplify quite nicely. It also looks like a triangle. Right angle triangle. Let's... Whoa. There we go. Go across like that. So A is somewhere up here. And C is somewhere out here. And B is above A, or above C, so maybe out here. And P is somewhere down here to minimize this distance. You know what it reminds me of? There's sort of a classic, it appears in a couple books on problem solving, and it was on the Manitoba Math Contest a couple of years ago as well. Can't remember what year, I want to say maybe the 2009 or something like that. But this seems to be the water to put out the barn question. So the minimum distance should be... Anyways, by the way, if you're not familiar with the question, it comes in lots of forms, but there's a barn on fire over here. There's a river with nice water down here. And there's a farmer over here who's got his bucket. And he needs to get to the river and then get to the barn to put it out with the water that he fills up in the bucket. What's the shortest path to do that? And the way this question goes, and I don't like the when they put this question on papers, because if you haven't seen it, it's really, really annoying to try and work this out on your own. But the idea is you first draw a better picture. The idea is you sort of reflect, because you're going to go one line here and one line there. You reflect this point, the barn in the riverbank. And the distance from A to P doesn't matter, but P to B is going to be the same as P to B prime because you've done this reflection. And the shortest distance between A and B prime is a straight line because the shortest distance between 2 points is a straight line. So the shortest the point P that minimizes the distance AP plus PB should be what minimizes AP PB prime. And you could write this up, you know, if you were going to, you could also probably use an arithmetic mean, geometric mean inequality to show this, but here's how I would briefly write this up. So, consider, because this is a C question, we should be justifying everything. Now, this is going to be for A, so I don't think it requires a whole lot of justification, but consider B prime at 0, negative B. The distance, let's say, and PB is equal to PB prime. And if you wanted to, you could actually use the distance formula here. It'll be difference in the x coordinates squared plus difference in the y coordinates squared. But of course, that's going to be the same as the square root of p minus 0 squared plus 0 minus negative b squared, because the negative b is just a b squared, and so that's pb prime. So okay, that's I would definitely write this. I wouldn't necessarily write this unless you wanted to. But okay, the shortest, the min distance AP plus PB is the same as the min distance of AP plus PB prime. And then I draw a little picture, as I already have, but I'll draw it again. B up here. Oh, okay, I'm doing this way too sloppily. A little firmer. I should probably keep a ruler with me. B prime, because my lines haven't been going straight for a while. So A, shortest distance, shortest AP plus PB is if P lies on line AB, or sorry, AB prime. And an explanation for this, you could say something like triangle inequality. So we want P to be on, really hard to draw a line freehand. There we go. We'll just fatten P up a bit. So imagine I had another point P prime. If that were somehow smaller, then I'd get something like this. We'd get a nice little triangle, but the sides two sides of the triangle always add up to more than the other side. So you could say by triangle inequality. And if you wanted to, you could say, you could do the full-blown, suppose there were another point that minimized it or was equal to the minimum, and then construct this triangle and then use triangle inequality. That would be fine, but I really don't think they're going to be looking for that. It's only C3, and we haven't even begun to answer A, although we're about to. Okay. So, this determines P, and X is equal to AP plus PB, which is, or PB prime, which is then equal to AB prime, which now I can work out. Because if I were to say, drop a perpendicular over here, you get a nice little right angle. What's this distance? It's C. C is here, and that's at 0C. No, it's at C0. C0. And what's this height? Well, this is going to be A, and then we go down a distance B, because B prime is at 0, negative B. So you could, as long as you drew this picture, say by Pythagoras. If you didn't want to use this picture, you could use just the distance formula and say, all right, what's the difference in the x coordinates? Well, it's 0 minus c squared. Sorry, this is at c minus b. So minus c here. Doesn't change anything, but we want to be correct because we want to earn marks. So you could say 0 minus c plus a minus negative b squared, and then you could say, well, then it's c squared plus a plus b squared, all square rooted. That would be fine, or you could say by Pythagoras because we've got a nice little right angle triangle here. Either way would be fine, and we've got our distance. We know what that minimum distance x is. Okay, great. Let's move on to b. If c is equal to 12, find all pairs AB for which a, b, p, and x are positive integers. All right, little more interesting, a little more advanced, maybe. I'm not entirely sure. I'm thinking Pythagorean triples involving 12, so I'm thinking 9, 12, 15. I'm also thinking 5, 12, 13, just because we've already seen the Pythagorean theorem come up, and we've got this square root here, so Pythagorean triples are already in my head. Will it necessarily be those values? I'm not sure, but it's possible. Okay, so first things first. X, an integer, means c squared plus a plus b squared is a square. So C, A plus B, X, E is actually a Pythagorean triple. Okay, that didn't take that long to show. Okay, so that's fine. But, so we need A, B, X, and P to be integers. So it's a Pythagorean triple since X, A, B are integers. So therefore A plus B is an integer. Okay. And A and B have to be positive integers. X will be a positive integer. They even, I think, said P is a positive. No, C is a positive integer, but P will have to be positive as well. Okay, so that's fine. Now the question is, what Pythagorean triples have 12? And I think there's only a couple. I really think it's just the two of them. But can I just say that and move on? That's a good question. So, So I might say if C is equal to 12, we need a triple with 12 as a leg. Legs are the shorter ends, shorter sides on a right angle triangle. Okay, so, well, we could just start listing out Pythagorean triples. That wouldn't be too bad. I think 5, 12, and 13, and 9, 12, and, no, there should be 12, 16, and 12, 16, and 20 should work as well. But 9, 12, 15, I think 12, 16, and 20 should do the trick as well. So I think these are the only ones, but let's make sure. So all Pythagorean triples look like k times u squared minus v squared, 2 times k times uv, and then k times u squared plus v squared. So this is a nice way to write out Pythagorean triples. You will get overlaps, I believe. Let me just say for non-negative. Well, you don't really use the zero case, so let's say positive. Integers, u and v. So this is a useful thing. If you haven't seen this before, it's a very useful way. You write out all the Pythagorean triples this way. You can get overlaps. I think there's a form where you will write out all the primitive ones, the ones that don't have a common factor. That's what this k is for, to ensure that you get all the multiples. But I think... So this is all we need. So every Pythagorean triple looks like this. So either 12 is equal to k times u squared minus v squared, or 12 is equal to 2k uv. So this one would mean that 6 is equal to k uv. And what could we have? We could have, k is also a positive integer. K could be 1, u could be, and u has to be greater than or equal to v. Well, greater than v. So we could have k is 1, u is, well, actually you could have u is 6, v is 1, that would be fine. We could have, well, let's do this on, I'm going to run out of space, so let's do this on another page. 12 equal to 2k uv, so 6 is equal to k uv. So you could have k is equal to 1, u is equal to 6, v is equal to 1. You could have k is equal to 1, u is equal to 3, v is equal to 2. You could have k is equal to 2, and then u is 3, v is 1. That's forced upon us. K is 3, u is 2, v is 1. Or k is 6, u is 1. Well, you can't have u is 1 and v is 1. So those are the only options, and then that would get, what triples would we get? We'd get, so u squared plus v squared, that would be 37. So there was a triple I didn't think of, 35 and 37. Can we just quickly work this out? So that'd be 1225 plus 144, just to make sure my formula is correct. We'd get 9, 6, 3, 1. What's 37 times 37? Because I don't have that memorized. 25, and then 0, 1, carry the 2. 11, so that's 9, 6, 3, 1. Okay, it works. And I got a triple that I didn't think would exist. So that's good. What else do we have? 3 squared minus, so that's 9 minus 4 is 5, so 5, 12, that's the 13 one. Let's see. 9 minus 1 is 8, so that's 16, 12, and 20. Already knew about that one. I'm going to suspect this one is 9, 12, 15. Okay, but what else could we have? Well, we could have k, so 12 is equal to k u squared minus v squared. And that's going to be a little harder to work out. Now, I don't think 12 is the... Oh, 12 is the difference between a few squares. So we could have k is 1, we could have u is 4, v is 2. That would certainly do the trick. What would that turn out to be? 12, 1, so 12, 16, and 20. I think that's the only way to make 12 as a difference of squares. You can't do something like 36 minus... Well, let's we could write out a few squares. So 1, 4, 9. When the difference between the squares is greater than 12, we know we can stop. 16, 25, 36, that's a difference of 11. So 49, that's the last one. That's a difference of 13. So nothing's going to happen with 49. That's 11. You would need 1 here. So that's not going to work. So nothing happens with 36. 25, you would need to go down to 13. That's not a square. That one works. Nothing else. So only 16 and 4 work. Okay, we could have k is 2, and then is 6 the difference between some squares? Well, again, if we look at our little chart here, no. No, we're never going to get that. What if k is 3? Well, is 4 the difference between some squares? And you could get 4 and 0, but 2 and 0, but that's not going to work, and that's about it. So that doesn't work. How about 4? Is 3 the difference between some squares? Yes, 4 and 1. So u is 2, v is 1, and this will give us 12, and again we'll have 16, and again we'll have 20. Okay, k being equal to 6, is 2 the difference between squares? No. K being 12, is 1 the difference between 2 squares? Only 1 squared and 0 squared, and that's not allowed. So, turns out we were missing one. 35, 12, and 37. Okay, so those are the triples. So now I know the possible x values. So, but I need to find all pairs A, B. Okay. So, what else could we do? And I might have approached this the wrong way. Maybe Pythagorean triples is the last thing we need to consider. But okay, let's talk about the A and the B. So, what do we have? P0 is on AB. We know that. So, and AB has the equation y equals to the rise, which is A plus B, over the run, which is C, x plus, and then A is the y-intercept. No, this shouldn't be... Should be minus a plus b. There we go. Yeah, alright, because then if I plug in c, I get the a's cancel and I'm just left with negative b. Okay, good, good, good. So, that tells me that 0 is equal to negative a plus b over c times p plus a. Or, and we know c is 12, so what could we do? We could have negative a times c is negative a plus b times p. So, minus ac over a plus b, well, actually just ac over a plus b is equal to p. So p needs to be an integer. So a plus b divides ac. Right? But I know the possible a plus b's. Okay? Each Pythagorean triple gives a plus b. So we could have, let's say, the 5, 12, 13 triple. A plus b is 5. Okay? And then we could have, so AC is going to be 12A. Therefore, A, say it like this. This is 12A. So A plus B is 5. So we need 5 to divide 12A. 5 is a prime. So we need 5 to divide A. So A is 0 or 5. Well, it can't be 0 because it's positive. And if it were 5, then B would be 0. And that can't happen either. So, let's say no AB pairs from here. Okay, you can't get a p-value that works. Okay. So, what else can we do? Well, we could try another triple. Let's try the 9, 12, 15 triple. So now A plus B is 9. So we need 9 to divide 12A. Well, there's already a factor of 3 coming from the 12, so we need 3 to divide A. So A could be 3, or 6, or 9, and therefore B would be 6, or 3, or 0. That can't happen. So 3, 6, or 6, 3 will do the trick. So these work, and then what's our p-value? P would be equal to so 12 times 3, so P would be 4 or 8. And then the x value would be 15. Okay, those seem reasonable. Let's try another triple. 12, 16, 20. A plus B is the other number that's left over, so I need 16. 16 needs to divide 12A. That tells me immediately 4 needs to divide A. So A could be 4, 8, 12, or 16. Of course, it can't be 16. So we could have 4, 12, 8, 8, and then, well, if it was 8, 8, what would we, so the A is 12, so we'd be looking at P is 6, because it would have to be halfway between the two, and, or 12, 4. And in this case, the X value is 20 for all of them. What would the P value be here? So it would be 3, or 6, or 9. Well, that's kind of cool. Kind of cool. And then what's the other one? Well, we could have 12, 35, 37. A plus B would be 35, which is really big. So 35 would need to divide 12A. 35 would need to divide A. No common factors between 12 and 35. So A is 35 or 0. Neither one will work. So the only pairs we're looking at are 3, 6, 6, 3, 4, 12, 8, 8, and 12, 4. And there we go. So 5 pairs, and we've figured them out. We've got all the pairs. Okay, and now C part. If A, B, P, X are all positive integers, so exact same reasoning, we should be looking at triples, Pythagorean triples. Prove there exists an integer n greater than 3 that divides both A and B. Okay. So, we know C is a positive integer. I don't know why they're saying A and B are positive integers again, because we already had that. Really, you should just have P and X are positive integers. We also didn't need that set again. But, okay, so I would think once again, C, A plus B, and X form a Pythagorean triple. Because of the way I did the B part question so generally, we can just import all our other results. So we got a Pythagorean triple, and we also know that P is equal to CA over A plus B. These are nice, neat, simple facts. Alright. So, I'm not sure how X being a positive integer is going to help us right now, but we'll see. But there exists an integer n greater than or equal to 3 that divides both A and B. Interesting. So, what can we say? Well, actually, this is I'm a little stumped here. So I want to use the fact that A plus B must divide CA. And we already saw earlier that all these things, all these A's and B's have a common factor that's at least 3. But how can we show that has to be the case? So I know A plus B has to divide CA. We can also see that A plus B divides C times A plus B. That's definitely true. So then A plus B must divide CB, because it's C A plus B minus CA. But I'm not sure that necessarily helps us either. Well, let's say... Oh, no, it's the A. It's the A there. So let's say something like, let D be the greatest common divisor. All we need to do is show that D, being the greatest common divisor of A and B, so we need to show D is greater than or equal to 3. Well, then A is going to be equal to D times something, let's call it capital A, and B is going to be D times capital B. So A plus B is D times capital A plus capital B, and the greatest common divisor of capital A and capital B is going to be 1. Okay, but CA is going to be C times D capital A. Therefore, for A plus B to divide CA, we need D, A plus B, to divide CDA, or rather A plus B to divide CA. Now, A divides CA, and no, what do I want to say here? So, A and A plus B, the GCD of A and A plus B must be 1. If not, otherwise, you know, let E be the GCD of A and A plus B. So A would, well, so E would divide A, E would divide A plus B, therefore E would divide A plus B minus A, which is equal to B, therefore E divides A and B, therefore E has to be equal to 1, because I already said the GCD of capital A and capital B must be 1. Now, since that's the case, that tells me that A plus B must divide C. Capital A plus capital B must divide C. Okay, so where can we go from there? Should we look back at the Pythagorean triples in some way? Well, yeah. So let C be A plus B times, what's a letter I haven't used yet? Have I used P or I don't want to use X. Let's say Y. Sure, Y. And then A plus B is capital A plus capital B times D, but this is going to force X to be divisible by A plus B as well. So capital A plus capital B squared must divide those. Therefore, it divides their sum. That's x squared, and therefore A plus B divides x. So what does that tell me? It tells me we're not looking at a primitive Pythagorean triple. Which I guess is true because the two primitive Pythagorean triples we had earlier did not work. And I wonder if it's an if and only if condition. That you get integers, you get A and B that can make P and X integers exactly if you're looking at a Pythagorean triple that isn't primitive. Is not a primitive Pythagorean triple. I forgot the key word there. Alright, so earlier, our primitive Pythagorean triple, so here the common value was 4. Here the common value to all of them was 3. So and then when we found these pairs, the A and B were also completely divisible by 4. So I'm wondering if capital A plus capital B is going to be their common factor. Except then it would have to be D, which is all the more confusing. Because we want to show that D is greater than or equal to 1. Not capital A plus capital B. Maybe it was just a coincidence. Because this D here, and this is capital A plus capital B. It's just a coincidence they turned out to be the same value. Okay. So I know it's not a primitive Pythagorean triple. Where does this go from here? Well, let's see. We know that these ones are positive integers. We want to prove there's something that divides both A and B. So, Therefore, if we divide each term by capital A plus capital B, we get another Pythagorean triple. It won't necessarily be primitive, but another Pythagorean triple. So we get, what do we say, y, d, and then I'm going to call it little x. But y and d and little x are all greater than 0, and no Pythagorean triple, I'm just going to use some common knowledge, no Pythagorean triple has values less than 3. Therefore, d has to be greater than or equal to 3. There's no way that d could be 2 or 1 because there simply isn't a Pythagorean triple that involves 2 or 1 and has positive values. And there we go. Alright, so we did have to use the Pythagorean triple. We did have to use x being an integer and p being an integer, and that was a nice question. I liked it. Alright, so we'll leave C3, and then we've got the last question to go. And that'll be all the way down here, C4. So we'll take a look at that in the next video. Until then, take care, have a wonderful day, and keep on enjoying math contests.